we get to this. So let's see. Let me try and recap. No, I'm not going to recap, but let me try and restate this line up here. This line right here.
Why would it not be negative f of a? Wait, it's the same thing.
Yeah, same thing. Yeah. I just wrote it backwards. Okay, so what's happening here, I really want to kind of re-stress the picture and the geometry of what's going on here. We have a function, little f, between some value a and some value b. And what we're doing is we're trying to find the sum of all these little infinitesimal rectangles, right? So there's a infinitely many little rectangles in here. If you were to look at one of those rectangles, right? One of those rectangles. The width of the rectangle is how much the x coordinate changes, right? That's your little change in x. So this is your little change in x. And this right here is how tall the rectangle is, which would be f of x, right? F of x always gives you the y coordinate, so it just tells you how high. So the area of that little piece would be the height times the width, right? So the area of that would be the height times the width, right? Height times width. Height times width. That's what we're doing, right? We're trying to see if there's a way to do like an infinite number of rectangles in here and somehow add up all these, right? So now I need to take a sum, don't I? I need to take a sum of these. So I need to now I need to add them up, right? Add them up. So to add them up, what I do is I do a sum. Y'all seen that notation before? Sigma? That means a sum, right? I need to add up all these things. I need to add up each of the rectangles. Again, this is just a very glossy overview of what we're doing. We're adding up each of those rectangles, right? Each one. But the big catch is that I have to have an infinite number of rectangles, right? So even more than this, I need to take some limit where I let the number of rectangles go to infinity of this sum. Oops, of this sum. Okay? But all that doesn't matter, because I just proved to you that the area is going to be what? Capital F of B minus capital F of A, right? Capital F of B minus capital F of A. So what notation should I give you to let you know that I'm trying to add up all these rectangles, height times width? I'm trying to add them up, but I'm trying to do an infinite number of them. What notation should I use for this? Maybe we should have like a special notation for it. The integral sign is the notation for that. That's exactly what the integral sign represents. It is this right here. This idea of taking the number of these to go to infinity. So I'm going to go back now to our integral notation, right? It was this. Right? That was our notation. Do you all see that this integral symbol represents the sum, right? It's a sum, but it's more than just a sum. We're going to take the limit as n goes to infinity. The number of rectangles goes to infinity there, right? And what is f of x dx? Well, f of x is the height of the function, and the dx is now this little delta x, but they're so infinitesimally small we don't call it delta x, we call it dx, because they're infinitesimal. That's the same. Do you see where the dx, what it means now? The dx is actually the width of this infinitesimally thin rectangle that you're going to add up. Y'all with me still? Okay. One more thing. We need to add something. We need to tell you where you're going to start and where you're going to stop, right? Where's your interval start and stop? Because if you're trying to find the area under a curve, you need to tell me where to start and stop, right? So these two numbers we throw in there to give you a starting and stopping point. This is called the definite integral. This is called the definite integral. And it's called definite instead of indefinite because you should get an answer, right? And that answer should be a what? Number. And that number should represent the area underneath that curve down to the x-axis. Pardon? Yes, I'm going to do that separately because that's actually the fundamental theorem of calculus, and then we'll put it all together. Right now, what I'm doing is I'm showing you where that notation comes from. The notation comes from the idea that we're trying to add up all these things, right? This is the area under F on the interval AB. That's what that notation means. Yes, this is the height of the function, right? We're trying to find the area underneath this function, right? We're trying to find the area under here. So what we do is we cut it into all these rectangles, right? If you take just one of those rectangles and look at it, the height is always f of x, and the width here would be, we'll just call it dx. It's how wide it is. And then the integral sign says what? Add up an infinite number of them. Now we need this because, as you're going to see later on in this class, what's in here is not going to be height times width. It might be some other formula. Because maybe we're not trying to add up areas of rectangles. Maybe we're trying to add up like volumes of things. You'll see. It's coming. Just the important thing is to understand that the integral sign is an operator. What it does is it allows you to take an infinite summation of things. All right? What's inside the integral, the f of x dx, is what you're adding up. In this case, height times width, area of a rectangle, right? Okay, definite integral, some more things. This right here is called the lower limit of integration. And this one is called the upper limit of integration. Upper limit of integration. How did that go? That's first time through. Did that make sense to, how many of y'all feel like that made sense, like where the formula comes from, how it tied to the mean value theorem? Just, okay, half, at least half, all right. You don't really have anything to compare it to, right, because I didn't show you the other way, but the other way involves Riemann sums, which is not necessarily, I'm not against them, I want to try something different. I wanted to connect it to the mean value theorem. In Riemann sums, you don't use the mean value theorem, so. All right, here we go. We need our final result so we can start doing some problems, all right? The final result, the thing you have to really take away from what I've said here this morning is this. With all that notation and understanding of what we're doing geometrically, we come to the fundamental theorem of calculus. Did you all know that there is a fundamental theorem of algebra? So in algebra, you need to take algebra. There's a fundamental theorem of algebra. It has to do with the complex zeros of a polynomial function. But algebra has its fundamental theorem. This is calculus, fundamental theorem, all right? All right, so here's what it says. And I should preface this, there's two versions of this theorem, depending on how you want to approach it. I'm using the second version, which is called the evaluation theorem, and it's the one we use the most, so this is the one I'm going to present. So here's what it says. It says that, well, let me put it up here, and then there are some conditions. What is that? What is that? Tell me what it is geometrically. The area under the function f on the interval AB. That's what that says, right? The area under the function little f on the interval AB. That is equal to capital F of B minus capital F of A. Boom, there it is. I always tell this story when I get to the fundamental theorem of calculus. So as a math major, you actually go back. I didn't know this when I became a math major, but you actually go back to the very beginning of math when you learn like 1 + 1 = 2, and like you learn all like the field axioms, and you go through everything rigorously, like with rigorous proofs. And you get to a point where you have to prove all the theorems of calculus that you learn in calculus. You have to prove them, right? Using what are called delta epsilon proofs. And so I can remember I had to prove this theorem, and it took me a while to prove it. I think it took me about 2 weeks to figure it out. Back then, there wasn't like Google, and there wasn't like Chegg, or what are all these things that are out there now? Is Chegg a thing?
Yeah.
No, not anymore. Whatever.
They were Mathway.
Yeah, Mathway. Like there weren't all these things. You can't go find proof. So we actually had to prove things, right? And you couldn't get tutoring too, because if you're a math major, there's an unwritten rule that you don't, like if a person is a math major and they're in like theorem proving courses, you don't help them. Like that's the whole point, is that they have to figure it out on their own. So I remember I figured this out, and I wrote down the proof on a whiteboard, and I was so proud of myself. I was going to see my parents that day. I put the whiteboard in the back of I had a little SUV, and then I got to my parents, and they're big old fluffy white, I forget what kind of dog it was. I don't know, it was big though. Anyways, I opened up the back of my car, and he thought I was taking him like to the park for like a run or something, you know. He jumps in there and like he races the whole thing, you know. But I had proven it, and by that time I knew the proof, you know, like I understood it. So every time I put it up here, I always think of that, you know, that dog just sitting there wagging his ass on my work and erasing it. Okay, so this is it. This is the fundamental theorem of calculus. All right, now we need to be explicit on certain things here. I mean, we need to talk about the connection between capital F and little f. We all understand here that capital F, if you take derivative, you get little f, right? In other words, capital F is the antiderivative of little f. And then also, we do have some conditions here. F must be what we call integrable. I don't think we've used that word in this class. Integrable. Now, think about it in Cal 1. In Cal 1, weren't there certain functions that were not differentiable? Like, you would have something like, if it had a sharp corner or a cusp, it would fail to be differentiable, maybe like a point. Well, for us to be able to do this, this function must be integrable. We need to be able to find the antiderivative of it, right? And there's some other conditions I won't get into, but basically, we need to be able to find the antiderivative for this to work, right? Not all functions are integrable. Not all functions are. But if it is, then we're in business, all right? Freaking awesome, right? Let's use it. So now I can officially say, at this point, everything else I said, well, you need to know the connections, but all that stuff, me trying to prove where it comes from, is irrelevant. Let's just use it. So let's find the area under a curve. First example, find the area under, and when I say under, I mean between the curve and the x-axis, okay? Between the curve and the x-axis. Find the area under f of x equals 3x squared on the interval 1 to 5. Now, I can go right to the fundamental theorem of calculus right now, but I'm actually going to draw a picture just so that we understand what we're doing here, right? We're trying to take this function between 1 and 5. What do I get when I plug 1 into this function? 3. So let's just say that that's 3. And what happens if I plug in 5? Oh, shit. 75? Okay, well, it's way up here. I'm just going to put it here. And this is a parabola, right? So it probably looks like this. Okay, we are trying to find the area from that function down to the x-axis. So if you imagine coming straight down, right? We're trying to find that area. What is it? Well, we have the fundamental theorem of calculus, don't we? The fundamental theorem of calculus says this for us. For that example, it says if we want to find the area, right, we're going to use the integral. We're going to go lower limit of integration 1, upper limit of integration 5. We're going to go from 1 to 5, right? And what's the function we're integrating? 3x squared. And then dx, we put dx. Dx has always been like what keeps track of our variable, right, in the past, but now it's actually the width of the rectangle, right? This is the height of the rectangle, this is the width of the rectangle. We're going to add up an infinite number of them, right? And the fundamental theorem of calculus says you don't have to add up shit. You just have to find the antiderivative, right? And then plug in 2 endpoints and you're done. So I need to find the antiderivative, don't I? So what we do here is, yeah, let me just do it right now. What we do is we're going to insert an intermediate step right here. Because I actually have to go find the antiderivative now, don't I? So we're going to insert this intermediate step where what we're going to do is we're going to just go find the antiderivative of the function first, right? We're going to find that. So let's go ahead and put that right here. What is the antiderivative of that? X cubed? That's it, right? Now, we're supposed to say plus c, aren't we? Yes. This is the only example I'm going to put plus c, but you're going to see from here on we don't need plus c. You'll see why. Plus some constant. That's the antiderivative, right? But wait a minute, I'm in the middle of this problem, right? I still need to plug in the 2 endpoints. So what we normally do, the normal notation is to put a bar at the end of this. We call this the evaluation bar. And what we do is we remind ourselves we're not done. We put the 1 down here and the 5 here. And this just reminds us that we have to take this antiderivative, we have to plug in the 2 endpoints still to get our answer, right? So now I'm going to say this equals, and now I'm at this step. I got to figure out what this is and then what this is. So what is capital F with B plugged in? Well, I've got to figure out what that is, right? And then minus, then I'm going to do capital F with A plugged in. So here's capital F, plug in B. 5 cubed plus C, right? Remember, you're plugging in the B, not the A. You plug in the B first. Then you subtract from that what happens when you plug in 1. 1 cubed plus C, right? What's 5 cubed? 125. I'm coming up this way because I'm out of room. So this is going to be 125 plus C minus, careful here, 1 minus C, right? What happens to the C's? They cancel. And that would happen every time I do this, right? Anytime I do this, I would always get the plus C to cancel, which means that from here on, when I do this antiderivative step, I'm not going to put plus C. I'm just going to put the antiderivative and act like C is 0, let's say. All right, so what's my answer? 124. That's it. That is a numerical answer for the area of this underneath this curve. Now, in terms of units, we don't know. Like if things were measured in inches, then we would say this is 124 square inches. If it was miles, 124 square miles, right? Something like that. Squared units because it's an area. Isn't that pretty?
If we change the notation, it's little f equals 124, or is it still?
Little f. Little f.
No.
This is the area under little f. This is little f, right?
Yeah. Basically, I'm just asking like what it is before the equal sign.
This to this to this to this to this to this. I'm not sure.
Like how we would use capital F of x equals the antiderivative of something?
No. No, because what we're doing is calculating a number, right?
Yeah.
And that number has a geometrical meaning. It's the area under the curve. It's not f of x or it's not capital F of x. It's just the area under that.
Okay.
So we just say this right here is the area, and it's equal to 124. Okay? What do you think? If you can find antiderivatives, you can find areas. Yes?
You said that the C's will always cancel?
Yes.
Right? Okay.
Yeah. Because do you agree that when we find the antiderivative, we're going to have plus c here, right?
Correct.
Right? And then when we plug it in here, we'll have plus c here. But when we plug it in here, this plus c will get subtracted each time. This minus will distribute to that c and get minus c.
So we're evaluating the antiderivative?
Yes.
What the evaluation bar?
The evaluation bar is saying we're evaluating this antiderivative at these 2 endpoints, or at these 2 points, which is what this says, right? Capital F is the antiderivative of little f. So the antiderivative of this at B, at that endpoint, and then the antiderivative of this at A, the first endpoint.
Got
It's pretty mind-blowing when you really think about what's going on here, because this is the graph right here of 3x squared, right? Okay, yes. The graph of this? I can show you the graph. But I want to draw them side by side first. That's little f, right? And we want to know this area. What we do to find that area, what we do is we actually graph what function? X cubed, right? What does x cubed look like? At 1, what's 1 in here? 1? What's 5 in here? 5 in here is 125, right? You plug in 5, you get 125. And so the area of this red is that distance. What's that distance? 125 minus that distance, 1. It should be really, I don't know, to me it's beautiful but also kind of crazy that this red area is just the antiderivative, the height of that point minus the height of that point. But that's what it is, okay? All right, so yeah, I actually have that one in Desmos right now. I don't know if this will help, but let's see if it comes back on. At least we can look over there. So let me get some things out of here. So we wanted the area right here, right, in the blue? And what it turns out to be is the, see, I have to graph them together at the same time. So it's a little harder to see it, but this blue area under here, this blue area is equal to the height of this point, which is the antiderivative. It's that height, which is 125. Take away the height right there, which is 1. And 125 minus 1 is 124. All right? All right. How are we doing on time? All right, so now we need to, let's do another example. All right? What's that? Let's see, how about we do one of the classic ones that I really like to show. How about this? So I want us to just take a step back and appreciate what it is I'm asking here. What is this asking you to do? Find the area between 0 and 2 pi of the sine function, right? So if you graph sine, which we all should be comfortable graphing sine, sine goes through one period, right? 2 pi. And I'm trying to find the area between the graph and the x-axis, right? So we're talking about trying to find this area and that area together, right? Trying to find what that is. That seems like an almost impossible question when we walked in here today, right? Without the fundamental theorem of calculus.
Add those together or see?
Well, let's see what happens. Let's see what happens, okay? Let's see what happens if we just follow the fundamental theorem. The fundamental theorem says, okay, I need to find the antiderivative of this first. Do you know the antiderivative of sine? Not derivative, antiderivative. Negative cosine of x, right? So I put that there, and then I draw my evaluation bar. I put 0 here and 2 pi here because I'm not done, right? That step right there just gives us an opportunity to actually find the antiderivative, right? And now I'm going to plug in the two things and subtract, right? I'm going to plug in 2 pi first, negative cosine of 2 pi, and then I'm going to plug in 0. Oh, by the way, I didn't put plus c, right? Do y'all see that? I didn't put plus c. It's going to go away anyway, so I'm just going to start putting just an antiderivative. All right, what is cosine of 2 pi? Cosine of 2 pi is 1, right? And then a negative in front. Minus, okay, over here, what's cosine of 0? 1, but then negative in front of that. So what do you get? Negative 1 plus 1, shit. 0. Damn it. What does that mean? What do you think this means? Doesn't make sense? They canceled each other out. Crap. That means that the fundamental theorem of calculus does not account for, when things go below the x-axis, it counts it as negative area. Yeah. Why? Why does it count as negative area? For us, it's area, right? For us, it's width and height, right? But for the formula, what is it? This is the height of the rectangle. When you go below the x-axis, what's your height? It's negative, right? And that doesn't know, right? That doesn't know. It's just adding things up. So it's looking at a rectangle. When it's looking at a rectangle over here, right? That rectangle, this will be a positive number, right? The height here, and the width is always positive. But when you're down here, that rectangle, it looks at the height as being a negative number, and then the width as being positive. So when you multiply these together, you get a negative. Yeah?
So wouldn't it be better to just take the area of the first one and then just multiply by 2?
Exactly, right? So what we could do here, because we really do want to know what that area is, don't we? We do want to know. So what we can use is our knowledge of the graph to say, instead of going from 0 to 2 pi, right, let's go from 0 to pi. And that'll give us the area of one, what we call arc of sine. And then from that, we could double it if we wanted the total area. So what does this integral actually give us? Does it give us a true area? No, it gives us like a net area. It gives you anything above the x-axis counts as positive, anything below is negative. So that means we may have to pay attention to where we have x-intercepts, right? Okay, I just want to point that out. Let's actually change the problem up. Let's go, okay, yes, this, by the way, this is the correct answer. If I put that on the board right here, if I present you with this problem right here, that's the answer. But if I ask you to find the total area, then you actually have to break it up and double the answer. All right, so separate question. Let's do it as a separate question. Find the true area between f of x equals sine x and the x-axis. So for that, what I'm going to do is I'm using my knowledge of what the sine function looks like. I'm going to go and take my integral from 0 to pi, right, instead of 2 pi, sine x dx. And then what did you suggest? Double the answer, right? So can I put a 2 in front of that? Yeah, can we do constants like that in front of integrals, push them in, pull them out? That's been okay in the past, right? Still okay. Nothing changes there.
So is that 2 being when we got the 2 pi that we originally had? Or
No, this 2 is just because I see that this and this, they're symmetric. They're symmetric. So what we're doing is we're going to pi, right? We're going to pi, and we're going to find that area, right? And that should give us a positive answer. And then I'm going to double it because this area should be the same as that area. I'm not pulling the 2 out. That's not what I'm doing.
okay.
All right, so let's do this. The 2 is going to come with us. What's the antiderivative of sine? We already did that, right? Negative cosine. So I'm going to put negative 2 cosine x. Evaluation bar 0 to pi. The antiderivative of that, I'm sorry, not the antiderivative, plugging in. Now it's time to plug in. So negative 2 cosine pi, and then negative 2 cosine 0. Any questions on what I'm doing there? What is cosine of pi?
Oh, one.
-1, right? Pi is over there. Cosine is the x-coordinate. So this should be -2 times -1, which is 2, minus, and then what's cosine of 0? 1 times -2. And so this should be 4, right? 4. Now, any questions?
Can you show us how you got with the -2 cosine phi?
Okay, what is the antiderivative of sine? Negative cosine, and then I just put the 2. So that's that, right? And then this is to remind me that I have to do the fundamental theorem of calculus, which means I still need to do something with this. I put this evaluation bar here, I put the pi and the 0 here from here. And now the last step is just to plug pi into this, that's this, subtract from it 0 into this, that's this, right? So as long as I've been doing this, I've always thought that this is a really weird result. Doesn't this seem strange to you? That the area underneath this curved looking piece right here is actually, well, what is the area of just this first piece? 2. The area is 2 there and the area there is 2. Doesn't it seem strange that that's a nice whole number? It's a sine curve. I don't know, it just seems weird to me that it's 2. But it is, okay, it is. Can't argue with it. All right, you all right? I'm wondering how far I want to push with this right now. Let's do one more, then I'm going to do something I think is pretty cool. How about this? So there's the graph of square root of x, right? And we are trying to graph that sorry, we're not trying to graph that. We're trying to find the area underneath that, right? All right, so the area underneath this, what do we need? Antiderivative, right? What's the antiderivative of the square root of x? Not the derivative, the antiderivative, right? 2/3 x to the 3/2, right? I'm doing power rule. This is x to the 1/2, and then I just add 1.